All right, let's take our familiar initial state of methane gas, 4.50 grams at a temperature of 310 Kelvin. Whoops, we also know the volume. It's occupying a volume of 12.7 liters. And again, that could be decimeter cubed. And it's undergoing an isothermal reversible this time expansion until the change in volume corresponds to 3.3 liters. And with this information, we can find the associated heat, work, delta U, delta H, delta T, delta V, and delta P. And so we'll exhaust all those possible questions. And before doing that, I just want to write in that N2 is equal to N1, and that's going to be 4.50 grams times 1 mole, which is 16 point, what is it for methane? Exactly. 0.43. Okay. And it is isothermal, so T2 is equal to T1, and that remains at 310 Kelvin. V2 will equal V1 plus 3.3 liters, and that was 12.7 and 3.3, which gives me 16.0. P2 is not known, but this is, one more thing to add to the given, and that methane is behaving as a perfect gas. Okay? In other words, it's not a van der Waals, or I don't have to work with the compression factor information. And therefore, PV and RT applies, and so N, R, T, N is constant, T is constant, so I'm not using any numerical subscripts, over V2. So I do know what my pressure is in the second case, and I notice that pressure is not given in this first case either. However, PV and RT still applies, so I'm just filling in what I can for the given and realizing that I have all of that information. Okay, so where should we start? The fact that it is both a perfect gas and an isothermal change should tell you something immediately. Well, let's go for the obvious. Delta T. So delta T is equal, of course, to 0, and that is because the change is isothermal. Now, because the system is this paper keeps bouncing up, because the system is perfect, and the change is isothermal, the only way that a perfect gas can change its internal energy is with an associated temperature change. And so since this perfect gas is remaining isothermal, delta U, therefore, is equal to 0. And so that's that one taken care of. Now, first law is always valid, and I'm writing it in this form here. But because du in this case is equal to 0, then dq is equal and opposite. I could put the negative sign on either one. dq is equal and opposite to dw. So essentially when I've found one, I've always found the other. So I think that dW, or the work, is a good place to continue. It is always the case that dW is equal to a minus pdV, whether it's reversible or irreversible. It's the way that we follow the integration now. That depends on whether it's reversible or irreversible. And work, therefore, is the integral of dW, and so the integral of this is equal to, there's some big clouds going by, so sorry for the lighting is going bright and dark, bright and dark. What I'm going to do is replace pressure with nRT over V, but I'm writing it like this to really pronounce the integral. I pull out, I don't want to forget the negative sign, I pull out what is constant nRT in front of my integral sign, and I'm left with 1 over V dV. Work, therefore, is equal to a minus, just wrote that twice, a minus nRT, and the solution to an integral of 1 over V dV is the ln of V final over V initial, which in this case is V2 over V1. People ask me sometimes, can we replace V final over V initial with P initial over V initial, and that is true only because it is perfect, so the PV-nRT works, and therefore that ratio works. And it works because it's isothermal, so only in the case of perfect and isothermal can you essentially do this, constant temperature, and relate pressure and volume inversely. But we know both volumes, so we'll leave it like this. And so we'll continue, we'll continue and do the solution. Work then is equal to, there's my negative sign, my N, I didn't actually calculate that above, so I'll rewrite it, 4.50 grams, excuse me, times 1 mole, 16.043 grams. Which value of R do you want? Do you want one that is joule per K mole or liter atmosphere per K mole? You can't take the ln of something with units, so this part here is unitless. And yeah, I think you would agree it's 8.3145 joule per K Kelvin mole. The temperature is 310 Kelvin, and then I'm left with the ln, and the ratio is V2 over V1, so I have 16 liters over 12.7 liters, and we want to make sure that you cross those out, because in principle you cannot take the natural logarithm of a number with its unit, so this is just a unitless ratio, of course it is. So grams cancel, as do the number of moles. That's unitless. Kelvin units cancel, and I'm left with the number of joules. It's very good to show that cancellation. You might want to do it, I don't know, with a pencil, so it doesn't get all cluttered up, and it's easy to check and identify that the unit remaining is indeed the one that you desire. And remember also, more importantly, I think, that any solution that you arrive at ultimately needs to be supported by a clearly demonstrated solution expression that includes values and units and unit cancellations that clearly shows the units of the solution. So, calculator time. 16 over 12.7 is this ratio, about 1/4, and we'll take the natural logarithm of that, multiply it by 310, and then again by 8.3145, and again by 4.5, and divided by 16.043. Carrying the negative sign, so it's 166.9982, and I want 2 sig figs on this answer. 166.99 joules becomes, it's too bad that wasn't 310 point, and I could keep 3 digits, but this is 170. So there's my W, my first non-zero. Does the negative sign make sense on the work? It does, right? Because this is an expansion, and Q and W, well, everything has a sign that maintains a system's perspective, and so energy is leaving the system as work for expansion, or work is being done on the surroundings by the system. A number of ways you can convincingly state that that value should be negative indeed. So 170 minus 170, and therefore, because Q is the negative value of work, they were equal and opposite. I can write then immediately, I don't need the plus sign, I'm just pronouncing the difference, is also 170 joules, but a positive value. So I'm going to just slide that down and continue my checklist. Let's go to delta H. It's usually the case that you need a delta U before you can calculate a delta H, and the reason for that is, and I say usually because if you did another problem where we did this one as a van der Waals, yeah, it was a little different. And we did delta U first. Okay, delta H equals what? The thermodynamic definition of enthalpy holds, of course, in all cases. So we have that H is equal to U plus PV, and therefore a delta H is a delta U, which in our case is 0, plus the delta of a PV. And what that is P2 V2 minus P1 V1. But because this is a perfect gas, I can exchange the PV for an nRT because they are the same. And that would be, what that implies is an N2 R2, well, R is a constant, T2 minus N1 RT1. But N2 and N1 are the same, R is constant, and this is also the same. So, yeah, there's nothing to, everything pulls out of the brackets, and there's no changing parameter left at all. And so, this is actually equal to 0. This we already established earlier is 0, and delta H therefore is also equal to 0. So there's no enthalpy change on this. Now why do I have a big shadow right there? Because the sun has just moved, so let's do that. A little better. Okay, and we'll pull this down and we've got this. So now delta V, of course, is given, and there it is, 3.3 liters. And now I want to calculate a delta P. And that's the last thing. Okay, delta P. Well, delta P is equal to P2 minus P1. And neither of those are given, but I have all of the other parameters, and I can use the ideal gas equation of state rearranged. P2 is NRT, and I'm not writing N2 and T2 because it's closed, so N is constant, and it's isothermal, so T is constant. But I will write V2, because of course it is an expansion, minus nRT over V1. And I can pull out nRT and put 1 over V2 minus 1 over V1. And let's put in some numbers. N. Again, I didn't stop and do that calculation of mass over molar mass, so I'll write it out again. 1 mole, in other words, I didn't actually calculate N, 16.043 grams, times R. So what value will you use for R? Should you use the joule per kmol or the liter atmosphere per kmol? Yeah, I'm going to end up with liters on the bottom, and I only want atmosphere, so in the answer, so I'm going to use the 0.08206 liter atmosphere value, kmol. Just a note about what I just said earlier about this not being calculated, and I could pull it down and just put in N like I did for if I had calculated it earlier. It's good that we're doing this the long way out for each one, because as a tutorial, we want to handle each of these separately. I'm going to let someone else answer that. Okay. Where was I? Temperature. 310 Kelvin. And hopefully that phone message is not for me. 1 over V2, 16.0. 1 over 12.7. And what I'm doing here is putting the units liter to the -1 on the outside of the bracket. Yeah. I'm just putting the operation inside the brackets because it's addition of a negative. So, grams, moles, Kelvin, liters, see, left with atmosphere. Delta P equal to. What do we have? 1 divided by 16, put it that way, minus open bracket 1 divided by 12.7, close bracket, equals. Now it's an expansion, and so V2 is larger than V1, and therefore 1 over V2 minus 1 over V1 is a negative. Multiply that by 310. Multiply by 0.08206, multiply by 4.5, and divide by 16.043. I have a negative value. We just saw where that came from. Let me get the number down. 0.11588. The units are atmospheres. We'll think about sig figs in a moment. Does this value make sense? This is the change in pressure. Do you think the pressure is going to drop in this isothermal reversible expansion of a perfect gas? It will, right? So you have your gas in the cylinder, and you're allowing that plunger get some room for it to expand. And if it does so but maintains the temperature, if you have the same temperature in a larger volume, you're going to have a smaller pressure. So yeah, that makes sense. A negative value. And let's fix the number of significant figures on that. And that should be 0. When you have 5, the convention is to go in favor of the even number. So I'm going to write this as an answer. I see where it comes from. And that's my delta P. And that's the end of the question.